let's take a look at 7.6. So 7.6 is very similar to section 7.3. We're going to be looking at equations that are equal to 0 and solving them. Usually we're going to be solving in a certain interval, so you don't need to put plus 2 pi n on the answers. I think almost every one of them says just find the answers within one cycle. Okay, so we're just going to have numbers, no plus 2 pi n in this section. What's different about how we're doing it from 7.3 is we're not going to be graphing. Okay, we're going to be solving them algebraically. We solved a couple problems algebraically in last night's homework, right? Where we had like sine squared x minus 1 equals 0. We added the 1 and took the square root. That's the kind of thing we're going to be doing here more. But we're going to end up with some problems that have 3 terms in them. And usually when something has 3 terms, and the last one is a constant, and the first one is double the exponent of the middle, that's a quadratic type of equation. So we're going to be using either factoring or quadratic formula. And it works pretty much the same way you would do it with numbers that, well, with things that weren't trig, just like you do in Algebra 1. All right, so some techniques that we're going to have to use. Factoring, I said, quadratic formula. I didn't say the one in the middle, but that's important too. When you're solving a trig equation, you don't want to have mixed trig functions. Okay, so if you've got sines and cosines in the same equation, that's not good. You can have all sines, you can have all cosines. You can have a cosine squared with a cosine, that's fine. But you can't mix sines and cosines together. So if they are mixed, you need to use an identity to get rid of them. I would say the identities that come up most often today are Pythagorean identities and the double angle. Half angle, you're not going to need. Sum and difference, you're not going to need those. Pythagorean and double angle, those come up. Okay. There's not really much more I can tell you other than just trying some examples. All right, so let's try this one. So this one is 2 cosine squared x plus sine x plus 1 equals 0. Now, it's almost a quadratic pattern. In general, something is a quadratic pattern if it's a trinomial. The last term is a constant. And the exponent that you have here is double the one you have there. So if that was like a 10, the one in the middle would have to be a 5. And you can still treat that like a quadratic, even though it's like an exponent of 10 and 5. It just has to be double. The problem with this is you have cosines and you have sines. That's like having 2 different letters. That's like trying to solve a quadratic that's 2x squared plus y plus 1 equals 0. You can't use quadratic formula on that because it's different letters. Okay? So what we want to do is get rid of one of them. My hint is to always substitute for the one that is squared. That is the one you always want to get rid of. Substitute for the one that is squared. Yes.
We should substitute it in with the with 1 minus sine squared.
Mm-hmm. Yep. We're going to change cosine squared to what we can substitute using a Pythagorean identity. Cosine squared is going to be 1 minus sine squared. Any question why we're doing that? Yeah? Yeah, now we're only working with sines, and we can turn this into a quadratic, factor it. It's going to be pretty straightforward from here. All right, so sine x is 1 equals 0. Okay, what do we have to do with that 2?
2 students.
Yep. So we're going to have 2 times 1, which is 2, plus 1 more. It's going to give me a 3. So I'm distributing and combining my constants in one step. 2 times 1 plus 1, 3. 2 times negative sine squared.
You could have negative 2 sine squared
Negative 2 sine squared.
plus sine.
Can we just bring that down? All right. So now, that is a quadratic type of problem. What it would look like as an Algebra 1 problem is this. Now, when I explain how to solve a quadratic in Algebra 1, I usually tell them you don't want this negative in front of the x squared, because everything you've learned about factoring always assumes the x squared is a positive. So whatever I would do here to get rid of this negative, I want to do the same thing right here. How can we get rid of that negative?
Multiply the entire side by negative 1.
Yeah.
Which will get you 2 sine squared x plus sine x, or no, minus sine x, and then minus 3 equaling 0.
Yeah. And now we want to see if we can factor it. Okay. If it confuses you to look at it with signs, then change the signs to x's. 2x squared minus x minus 3. But I kind of want to get used to trying to factor it with the signs, so we don't have to do that stuff. So we're going to need 2 sets of parentheses. What would be my first term in each set? Yeah.
The 2 sine x.
2 sine x and
Sine x.
sine x. So it's just like having 2x and x.
The 2 sine x needs to have the addition one, because we know that the sine x is like less than.
So you're saying we need what kind of signs? Both positive, both negative, or one of each?
One of these.
Yeah, we need one of each.
The positive is going to be over on.
I think the positive goes there.
No, that's where the negative.
Oh, that's what. Okay.
Because if the.
All right. Well, let's try it and see. And now, what about 2 numbers that multiply to give me 3?
3 and 1.
3 and 1. Let's check it. So 2 sine x times sine x is 2 sine squared. 2 sine times 1 is 2 sine x minus 3 sine x. What's 2 sine x minus 3 sine x?
Negative sine x.
Perfect. So we factored. Okay. Now, some problems in the homework are going to start you at this step. It's already going to be factored for you. Now you just have to take that and do something with it. When you have something times something equals 0, what do you do? Yeah. You set each factor equal to 0. So you have 2 sine x minus 3 equals 0. Sine x plus 1 equals 0. Now some problems in the homework will even start you at this step. They'll just give you this as the problem and say solve for x. Okay. So the hardest kind is when you have to do your whole thing. You've got to factor it, you have to set it equal to 0, and you have to solve it. Now we're at the last step, solve. Okay. What's the sine of x going to equal here? Yep.
1.5.
Yep, 1.5. Now you can, well, you tell me what would be the next step now to get rid of sine. Yep. You would take the inverse sine of both sides, but this is 1.5. Where does the sine function hit 1.5? Yep. It doesn't hit 1.5. So in this case, this part of the problem has no solution. Okay, so there's no answer from this part. We still have to finish the other part. Okay, so no solution there. So sine of x equals -1. You can do inverse sine, but that's where the graph hits the low point. Where in the first cycle, do you hit -1? Yep.
It's going to be at, if I remember correctly, 3 pi halves.
Yeah, 3 pi over 2, or 270 degrees. Now, if you do inverse sine of -1, the calculator is going to tell you -90.
Then you've got to add the 360.
Yeah, they didn't say they wanted answers that were negative. They wanted the answers in the first cycle. So, just like we learned way back, if you get a negative number, you can always add 360 to it to make it positive. Okay, so the only answer to this problem is 3 pi over 2. Had this worked on the left-hand side, we would have gotten 2 more answers because sine is positive in quadrants 1 and 2. But that doesn't work.
So like if that other thing you say you get the solution to that and you so there'd be 3 answers?
This would have had 3 answers if that part worked. Yep.
Okay.
I'm pretty sure it would actually only had 1 because, oh wait, no, it would have 3 answers because it.
Yeah, it would have had 3. Right, let's try this one. So find all solutions in one period. Now this time they don't even tell you what the period is. You need to figure that out. I'm not going to go through it from scratch because we've already done it. But the period of sine squared, that's sine to an even power. The formula is pi over b. So the period of sine squared is pi. Period of cosine to an odd power is 2 pi over b. What's the least common multiple of 1 pi and 2 pi?
2 pi.
2 pi. Yep. So it turns out that the window you need to look in is the same as the last problem. Most of the time it's either 0 to 2 pi or 0 to 1 pi. That's what usually happens. Okay. So it says to find all the solutions to this. What do we have to do first to make that equation look more like the one we started with on the left? That's the first thing. Yep.
Change the rate to sines. So it's 0 though?
We want to get it to 0, yes. We want to get it equal to 0.
I thought you said like only one trigonometric function. So like,
Well, that's going to be after we get it equal to 0. Let's get it to 0 first. So how could we get it equal to 0? Yeah? You could subtract the 1 plus cosine and move everything to the other side. I'm going to put everything on the right side. For a very important reason you'll see in a second. You might be thinking, well, I thought you said you wanted the squared term positive. I do. So I'm going to put it on the right side. Okay, watch what happens. So if I move it over, I have -2 sine squared x plus cosine x plus 1. Any question on, maybe not why I put it on the right side, but how? Okay, now you're going to see why. We have 2 different trig functions there. Which one did I say to always substitute for? Yeah. Yep, substitute for the one that's squared. We're going to substitute in something right there. What is sine squared equal to? Yep. 1 minus cosine squared. Now, what do we have to do? Yeah.
Negative.
Do what?
Get rid of the negative.
Okay.
Or no, distribute.
Distribute. And when you distribute, what's going to happen?
It'll get rid of it.
The cosine squared is going to become positive. That's why I put the cosine squared on the right side, because I knew that was going to happen. If you didn't know that was going to happen, it's not a big deal. It's going to end up negative, and then you're going to multiply everything by -1. But I just avoided that. So distribute that out. What's -2 times 1?
-2.
-2 plus 1. -1. So my constant is -1. What's -2 times negative cosine squared?
2 cosine squared.
2 cosine squared. And then just bring down your cosine. Alright. So now we've got 3 terms. The third term is a constant. All the trig functions are the same, and that exponent is double the middle. So that's a quadratic equation. Right, let's try factoring. If it doesn't work, we're going to have to use the quadratic formula. Okay. What would be my first term that I would put in each set of parentheses? Yeah? 2 cosine and cosine. What about my, I won't say signs because that's confusing. What about my symbols? Positives, negatives, or one of each?
Negatives.
Well, if they're both negative, then a negative times a negative is going to be a positive.
We've
For
got
the
to have
constant.
one of each.
Right. We got to have one of each. And which one do you want to try in the first one?
Let's try positive.
Okay, let's try positive. And 2 numbers that multiply to give me 1. Yeah, 1 and 1.
We're going to have to swap the signs.
Yeah, let's check it. So 2 cosine times -1 is -2. -2 plus 1 is not what we want in the middle. So we need to switch the signs. Now we've got 2 cosine times 1, that's 2. Minus 1. 2 minus 1 is positive 1 cosines. Perfect. Okay, so now we factor. And again, some questions in the homework are going to start in here. So the factoring is already done. Okay, once we factor it, what do we do with each factor? Yep. Set them equal to what?
0.
Yep, set them equal to 0. So on the left, cosine x is going to equal 1/2. On the right, cosine x is going to equal -1. Everything's going to work here. There's no error that you're going to get because this number is not bigger than 1. So we're going to get solutions from all this. Okay, let's start with the one on the left. That's the harder one. We're looking for where cosine is a positive value. Where is cosine positive? Yep. 1 and 4. We need to find the answer in quadrant 1 first. How do you get rid of cosine?
Inverse cosine.
Inverse cosine. So we need the inverse cosine of 0.5. 60 degrees. Once you get the answer in quadrant 1, what do you do with it to get the answer in quadrant 4? Yep, Sophie. Subtract it from 360. So we get those. And now, cosine x equals -1. I think we just did that one. Where does cosine hit the low point? In the first cycle. Yep.
270.
270. And of course, you could change all those to radians if that's what they wanted. 3 pi over 2, pi over 3, 5 pi over 3. And that's it. Those are all the answers to this problem. Yes?
Can you just show how to get rid of the sign again? Because you had the sine squared.
So we use the Pythagorean identity sine squared plus cosine squared equals 1.
Yep.
Solve it for sine squared and substitute.
I don't understand that.
So solve it for sine squared. And now, using what the Pythagorean identity tells you cosine squared is, substitute that for, oh, I solved it the wrong way. Using what the identity tells you, take what sine squared equals and fill it in right there. You can solve it either way. It depends on what your problem needs you to get rid of. We needed this one. Yeah. Question on that one? Okay. So just a reminder, you really don't need to write this down. When you're looking for all solutions, you have to put the plus 2 pi n on your answer. In this section, we're not doing the plus 2 pi n. Okay, so I'm just reminding you about that. If we wanted all solutions to the last problem, I would have put plus 360n on each of these. But the direction specifically said in one period. Okay. And that's pretty much what all the directions are going to say in this section. One period. Yeah.
So if there's like an imaginary, would you still have to figure it out, or you just call it like no resolution?
No, we won't deal with imaginary. So if you end up with something like
Sure, never
sine
mind.
was over 1.
if you end up with something like that, you now have to take the square root of both sides, but the square root of -1 is imaginary, so we would just stop.
Okay, so you
We don't deal with imaginaries. No. That will happen at some point. Yes. The last one? Yeah. So yeah, that's just a reminder of how you write all solutions. Because I want you to really remember that there are infinitely many solutions to these problems. We're not writing them that way. Okay, let's try this one. Now, when you first look at it, it doesn't look like it. The first two did. It doesn't have anything squared in it. But it will, if you solve it correctly. It's going to end up being exactly like the first two, except I don't think it's factorable. One step at a time. You're going to have to use an identity here that we've used before. Does anybody know what we're going to change in that equation? Yep.
Let's turn the 3 cosine x into... Let's change 3 cosine x into the other version of itself, so it's just sines and cosines.
Okay, I think we should change it to just sines and cosines, which means we should leave the cosine alone. But we should change something else that's not sines and cosines.
We could
Can we change the tangent to sine over cosine?
We can change the tangent to sine over cosine. And that's the whole key that's going to lead you to end up with something squared. Okay. So does anybody see what we could do now? We would get something squared. Yep. Yes. And then it turns into a problem just like the last two. Multiply both sides by cosine. Cosines are gone. We get sine x equals 3 cosine squared x. Now we have to get it equal to 0. So what side should I put everything on? Do I want to put everything on the left? Or do I want to put it all on the right?
Right.
We want it all on the left. Remember what's going to happen. When you do a substitution for this cosine squared, you're going to be substituting in something negative. So if you put everything on the right, you're going to make this negative. If you put everything on the left, it's just going to be one less step you have to do later. Okay, so this is what I would do. Cosine squared. Okay, so now we got that. And what can you substitute for cosine squared? Jake? 1 minus sine squared. Exactly. Okay. What do we need to do with the -3? Yep, let's distribute and write it in the order that a quadratic normally would be written. That's going to give me a constant of -3. -3 times negative sine squared. That's why I put it on the left. 3 sine squared x. And then just bring down your sine x. Now, that's not factorable. 3x squared plus x minus 3. Come on. I don't think you can factor that. If you think you can, let me know. But I don't think you can. So, we're going to solve this with quadratic formula. If you were solving this with quadratic formula, what would you be solving for? Yeah.
The zeros where it intersects like where it goes through the axis.
So like when you write your answer, you would write this equals and then you get the number. So what's the thing you're trying to find? You're solving for, and I'm not going to say it as x, I'm going to say you're solving for the middle thing, which in a quadratic happens to be an x. You're going to do the same thing here, but you're solving for the middle thing. Just like you do in a quadratic. You probably never thought about it that way, but that's what you're doing. You're solving for the middle thing. So whatever you get for an answer when you do the quadratic formula, you take that answer and you set it equal to the thing that's in the middle. In this case, you're done. It's just x equals whatever. When we solve ours, it's going to be sine x equals. And then we write the number. Okay? And then we have to get rid of the sign with inverse sign. But let's go through the quadratic. Okay. What's a going to be?
3.
3? B?
1.
1?
-3.
Yeah. It's exactly the same steps as that other one. Yep.
So when you have when you have the a squared plus bx plus c, you turn it into the two parentheses. Is that like called completing the square?
We could complete the square.
Is that the name of it when you do the two parentheses?
No, that's factored.
So okay, so when
Yeah.
you factor in, you set that to 0. You're in like a normal quadratic equation. You're finding where that equation crosses the x-axis.
Yeah.
Okay. So it's like those numbers, the exact numbers that you get from solving it out.
Those are the x-intercepts.
And so if you solve this out completely with the plus or minus thing, that's where it would cross the x-axis.
The x-axis.
Okay.
Yep. Okay, so just make sure I did that right. Negative b plus or minus b squared minus 4ac all over 2a. Perfect. Okay, so -1 plus or minus, those are going to cancel. What's 4 times 3 times 3?
36.
Plus 1?
37.
Okay. Now, if you were doing quadratic in Algebra 1, you just say x equals, and those are your two answers. This is not x equals. This is sine x equals. Okay. So what I would do now, just to make it visually easier, I would separate it into two problems. One with a plus, one with a minus. So sine x equals -1 plus root 37 over 6. And sine x equals -1 minus root 37 over 6. All right. Now, let's think about the one on the left. The square root of 37 is a little bigger than what number?
Squared. It's
A little bigger than 6.
A little bigger than 6. So if you take like 6.1 and then you subtract 1 from it, 6.1 minus 1 is a positive number. The top is positive. The bottom is positive. Positive divided by positive is a positive. This whole number is a positive. Sine equals a positive. Where does that happen?
It's gonna happen on the top half, so we know it's between 180 and 0.
So yeah, that problem is going to give you answers in those two spots. Now, this problem,
It's gonna give you the answer below.
yeah,
So,
-1 minus the square root of 37. That's a negative number. A negative number divided by a positive number is a negative. So, as long as we don't get an error, meaning these numbers aren't above 1 or below -1, the other two answers should be there. Okay? So let's start with the top one and just see what we get. So let's take the inverse sine of, I'm going to do it like this, -1 plus the square root of 37, and then divided by 6. I think that should be okay. Yeah, it should be okay. Okay, 57, we'll call it 57.9. There's your quadrant 1 answer. How are we going to get the quadrant 2 answer? Yep.
180 minus.
180 minus the answer we just got, 122.1. Okay, so there's two answers. Now, has anybody noticed anything about the other one yet? If you take -1 and minus the square root of 37 from it,
it's going to be greater.
-7, just call it even -7. If you take -7 and you divide by 6, what's going to happen here? Which is not greater than 1. It's
Less than
It's less than -1. That's a problem. You can't take the inverse sine of a number less than -1. So if you even try to do this, you're just going to get an error. So there's no solutions from this part. So these are the only two solutions in this problem.
I know that for the most accurate answer, you go from degrees to radians, but like, what in the problem can like signify if it wants to in degrees or radians?
The
Like,
directions. It'll say write in degrees or write in radians
For
on
this-
the test.
For this, would it still be correct if you did it in radians? In the calculator.
Technically, my answers are wrong because it did specifically say in this problem to do radians.
How? Oh, okay. Good point. Yeah.
So, I mean, that's okay. I mean, all I have to do now is change those degrees to radians, which I should do.
But you'd be less accurate if you did it directly in the calculator, like you just did the mode in radians. Right? What I mean is like where
You would have gotten the same level of accuracy on this problem. It wouldn't have mattered. So 1.01 is what the top one would have been. And the bottom one, 22 multiplied by pi. Yeah, I think it would have been easier to have the calculator in radians, then I wouldn't have to do all the stuff I'm doing right now.
But when are we supposed to do the degrees to radians for like accurate answers? I remember that was something.
So that's only if they ask for an exact answer.
Oh, like for up to this many like decimals.
Yeah, you cannot get exact answers to this problem.
God, yeah.
Is there any question how I changed the degrees to radians?
Not for this one, you're filling out quadratic formula. Why did you write C?
So, what number do you think is wrong?
C. Would you be positive 3
It was a minus, but I canceled it with the other minus. Because that was a -4. So it was minus a minus, so it becomes a plus. Okay. So I would make sure you read pay attention to the directions. If it says to do the problem in radians, I think it would have been quicker to just have gotten these answers originally, rather than have to take the degree answers and now change it at the end because we forgot to do it. But it's up to you. You can do it either way. There's really nothing new in this problem that you haven't seen. You're just going to move everything to one side and substitute for cosine squared. Is there any question on that? I think the first three problems cover what's going to happen there. Yeah?
When it says in one period, does that suggest that it wants radians?
No, it doesn't suggest anything. This problem, I would accept degrees or radians. Because it doesn't say, it depends how you define your period. You're going to define it 0 to 2 pi, or you're going to do 0 to 360. You could do it either way. On the test, it won't be vague like that.
Okay.
It'll say degrees or radians. Yeah. So this one is definitely radians. Let's try it. What do we always want to make sure we get it equal to first? We get it equal to 0. Do you think I should put everything on the right? Or should I put everything on the left? Yeah? Yes. I would put everything on the left because you're going to be substituting for the squared thing. Oh no, you want to put everything on the right. Yeah. It wouldn't really matter. You just have to multiply by -1 to fix it. But the identity for secant squared, which you're going to need in a second, is 1 plus tangent squared equals secant squared. Okay, so put everything on the... Well, let's try the right and see what happens. If we don't like it, we'll multiply by -1 and fix it. So we got 3, -3. Tangent to the 4th x plus secant squared plus 1. Now, we can't work with tangents and secants in the same problem. This is a quadratic pattern, though. It's 3 terms. The last one is a constant. And this exponent is double that one. So that means it's either going to be factorable, which this one will be, or a quadratic formula. But we can't work with secant squared. So what can I substitute in for secant squared? Yep. Yep. And I don't like the negative here, so I wish we had put everything on the other side. So I think you were right anyway. So we're going to change secant squared to 1 plus tangent squared. So you're going to have 1 plus tangent squared plus 1. What's your constant going to be? 2. 1 plus tangent squared plus 1. That's how I got the 2. Okay. So I do want to multiply everything by -1 because it's going to be better. So we're going to do that. Sometimes it's a little tricky to figure out what side should you really be getting everything on. And if you put it on the wrong side, it's not a huge problem. Okay, so now this problem is pretty much like this. That's a quadratic pattern, and that is factorable. If it's factorable, you can avoid quadratic formula. Okay, so what? Let's factor this one. And then we'll change it back to tangents after. Okay. What would be your first terms in each parenthesis to get 3x to the 4th? Yeah?
3x squared and 3x squared, or 1x squared.
3x squared and 1x squared. Yep. what would your signs have to be?
It would have to be a double negative.
No, right there. One of each.
One of each.
Right, it would be one of each. We just have to figure out which one we want to put where. Let's try plus and minus. And now two numbers that multiply to give me 2.
That'd be 1 and 2.
Let's try it that way. That's going to give me 3x squared, take away 2x squared. No. So I have to switch my signs. Now that gives me negative 3x squared plus 2x squared. Negative 3 plus 2 is negative 1. Okay, so that is how you factor. But really, we weren't working with x. What were we working with?
Theta.
No, not theta.
We were
Tangent. Okay, everything was really tangent. So it really factors is 3 tan squared x plus 2 tan squared x minus 1 equals 0. That's how you factor it. Let's start with the left one. What do we have to set that equal to?
0.
You've got to set it equal to 0. When you set the left one equal to 0, what number will you end up with on the right?
we'd have negative 2 over 3.
Yes,
That's real.
because you'd have to minus the 2 and divide by the 3. Now, what would be your next step here?
Square rooting.
You would take the square root of both sides, but what's going to happen when you do that? Yeah, that's going to be imaginary. So we don't have to continue here because there's no answers from it. Now we can go to the other one. When we set tan squared x minus 1 equal to 0, and we put the 1 on the other side, what's going to be right there?
1.
Now, what would we do on both sides? Square root, yep, which we can do.
Which would be plus or minus 1.
Yep. So we're looking for where the tangent equals, if you want to separate it, positive 1 and negative 1. Now, we want to keep in mind two things. The ASTC chart and the fact that our answers have to be between negative 90 and 90. That's what they said. Or negative pi over 2 and pi over 2. Okay. What's the inverse tangent of 1?
That's going to be 45 degrees.
Yep. 45 degrees, or pi over 4, which is definitely between negative 90 and 90. Now, think about the other answer. Tangent is positive here and here. Your answers have to be between negative 90 and 90. If you do 180 plus 45, are you going to get an answer between negative 90 and 90?
No.
No. Then you can ignore the other answer because they said to. You don't need it. Now, what's the inverse tangent of negative 1? Yep. Negative 45. And the same kind of thing is going to happen. You can ignore the other answer because it would be in quadrant 4, but that's way outside negative 90 to 90.
You've got to keep the answer on the right side of the
Yeah, we gotta keep the answer here, negative 90 to 90, and that's exactly what those two are. Any question on that one? Yeah. Pi over 4, that's 45 degrees in radians. That's the inverse tangent of 1. 45. Alright, so the last one. Nope, I'm going to do that one. Let's try that one. So this will be our last one. What's going to come up here that we learned yesterday? Yeah. you got to get rid of this 2. And the only way to do it is with the identity. What is sine 2x?
2 sine times cosine.
2 sine times cosine equals sine. Okay. Now, what do you always want to get it equal to?
0.
Yeah. I think the easiest way this time is move everything to the left. Now tell me what you could do on the left side. We've done this today, but this is an easier version of it this time. Yeah?
Well, could you subtract the sine x from the 2 sine?
No, those aren't like terms. That's like 2xy minus x. They're not like terms. But you can.
Can we change the cosine to a sine?
No.
Not without messing with an argument, so no. No. Yep.
So I can't, I might be repeating what Jack said, but like the whole secant identity.
No, we're overthinking. What do both those terms have in common?
Sine.
Yep.
Use the double.
So what do these both have in common? Yeah? Factor out sine. The goal when you're solving a problem equal to 0 is always to factor it. If you can't factor it, you have to use quadratic formula, but there's no squareds here. So the only way you can solve it is you've got to factor it. If you factor sine x out of the first term, what are you left with?
2 cosine.
2 cosine x. And if you factor it out of the second term, what are you left with?
-1.
Now set each factor equal to 0 and solve. Sine x equals 0. Okay, I think we've done this one earlier. Cosine x equals a half. We go back and just look at our notes. Yeah, cosine x equals a half. We already solved it. 60 degrees and 300 degrees. Alright, so let's write that down. And they said 0 to 2 pi, so pi over 3. That's, oops. Pi over 3 is 60. 5 pi over 3 is 300. And think of where does the graph of sine cross the x-axis? Where is it equal to 0? Yep.
Pi.
Pi and
2 pi. Or 0.
0. Yeah, we don't want to include 2 pi in the answer, even though it is correct. It has a parenthesis on it. So we don't include the 2 pi, but you do include the 0. Yep. And there's your 4 answers. Right, so 7-6 has a lot of stuff going on in it, right? A lot of algebra stuff tying in with trig. We can practice a few more in the warm-up or in the homework tomorrow, but that pretty much covers the kind of stuff you'll see in the homework. Oh, we pretty much got it. Let me double check that. Okay, not all of these problems you have to even factor. Most of them start you with the factored version, so it's going to be quicker. Yeah, I think that's fine.